Okay, can you see my screen?
Yes, we hear you well, please.
Okay, thank you very much. Good afternoon. My name is Daria Gordeeva. I present to your attention a report on the topic vertical horizontal model of states of software with injected effects. First of all, I want to say a few words about the concept of injection of software defects. This is not a new concept, but well known. It is used to assess the quality of fault tolerance mechanisms and the quality of testing. Defects are injected into the software in accordance with the profile, and then the software with injected defects is tested. After that, the obtained results are analyzed and type of profiles are formed. Analysis of profile residuals allows you to make a decision in terms of increasing the level of fault tolerance or improving the quality of testing. Existing works devoted to an approach based on an injection of software defects can be logically divided into several following groups. The first group is works that are devoted to tools which describe their functionality and advantages. The second group of works is devoted to features of the applications of the software defects injection and its optimization. And the third group is works that are devoted to general approaches and concept of defect injection. And the fourth group is works that consider modeling the process of software defect injection at various development stages, including partially Markov models. It should be noted that there are no works in the field of software defect injection describing behavior of software with injected defects, included the number of injected defects and the variable number of active states. In this regard, the goal of this research is to describe states and transitions between them using Markov chain. On this slide, we introduce the basic concepts and types of software defects profiles. A profile of software defects, it's an ordered set of faults or defects consisting of taxonomy of a profile of software defects and specific defects that correspond to it. Misalignment of the profile of software defects is the inconsistency between types of defects profile in part of specific software defects. For example, between the profile of injected software defects and profile of discovered software defects. Forecasted defects profile is a profile of defects which represents the correspondence between the predicted taxonomy of software defects type and the real defects, the number of which corresponds to the predicted number of software defects. Injected defects profile, this is profile of defects, which is a subset of the forecasted defects profile. Real defects included in this profile are injected in the software. Profile of all discovered defects, this is profile of defects that were detected during software testing. Profile of newly discovered defects is profile of defects that were detected during testing and were not injected. Profile of discovered and injected defects. This is profile of defects that were detected during testing and were previously injected. And profile of not discovered and injected defects. This is defects that were previously injected but were not detected during testing. On this slide, we show formalized representation of software defects profile and variants of misalignments. Yes. Next, we will present and describe such misalignments in more detail. Combination of EPD profile and PADD profile, EPD profile, IPD. This injected defects profile and profile of all discovered defects represent all misalignments of profile of defects. The forecasted defects profile is required to present injected defects profile. All other options of profiles are a result of combination of injected profile defects and profile of all discovered defects. We will present the possible variants of misalignments of profiles in a formalized form. This is 10 variants of misalignments. Next, we will present and describe the model of software states with injected defects using Markov chain. The Markov chain is a like previous reporter said, in this case is presented as a sequence of transitions of software from state to state which are incompatible. Therefore, the considered Markov chain contains 4 states. First state is ideal software, second state is software with injected defects, third state is software with own defects, and fourth state is software with both own and injected defects. Next, we will present the topology of the directed graph in the form of an adjacency matrix. Therefore, taking into account the adjacency matrix, the matrix of transition probabilities is written in the following forms. The Markov chain at any stage k can be characterized by a column vector that is column vector by the distribution of probabilities over the states chain at the state k in the general form, and therefore this column vector of probabilities distribution on the initial states looks like here. And if P is the current probability distribution, then the distribution can be determined in the next step by the multiplying the vector by the transition matrix. From the associativity of matrix product, it follows that in order to find out the distribution of probabilities through the M steps started from case step, it is necessary to multiply this matrix to this vector. As already defined, the model of software states with injected defects generally consists of 4 states, and more detailed analysis of this model made it possible to clarify it and formulate the following statements. Each model has an additional attribute. This is software defects injection level, DIL. The injection level of software defects reflects the number of injected defects in the software. This attribute affects the model, including the number of active and inactive states of the model. Note that additional index was introduced to indicate the vertical of directed graph. When this index equals 0 before defects are injected in the software, the active states include the state of ideal software and the state of software with own defects. And the state with injected defects and injected and own defects are inactive. When this index bigger than 0 after the injection of software defects, the state with injected defects and the state with injected and own defects are active, but the state of ideal software and the state with own defects are inactive. Each active state indicated by a solid line, in addition to the ideal state of software, can be detailed into several following states. This is normal state, false state, and failure state. We will present and describe the graph of transition at deal index equals 0. This figure shows the transformation of the graph of physical state into the graph with transition probabilities. Active states are indicated by a solid line and inactive states by a dotted line. The topology of the directed graph in the form of adjacency matrix is presented in this table. Taking into account the adjacency matrix, the matrix of transition probabilities is written in the following form, and our vector of probability distribution for the initial state will have the following form. So a result, we will get a distribution of probabilities through the M steps, starting from the case step. And on this slide, we present and describe the transition graph for index deal equals 1. This figure shows the transformation of the graph of physical states into the graph with transition probabilities. Equal states are indicated by a solid line, and inactive state indicated by a dotted line. If we take into account the adjacency matrix, the matrix of transition probability is written in the following form, and use vector of probability distribution, we receive as result distribution of probabilities through M steps started from the case step. As conclusion, as a result of this work, carry out a model of states of software with injected defects and transition between them using Markov chain was presented. In this case, the number of injected defects which affected the set of active and inactive states was taken into account. The result obtained made it possible to determine the distribution of transition probabilities between the designed states. And in the future, it is advisable to apply this result in the development of tools for injecting software defects or modeling real case of injecting. Thank you very much for your attention. If you have a question,
thank you very much. Thank you very much, Daria, for your presentation, for your very interesting talk. And now we have time for a question.
Please. If I can ask one question. Thank you, a very interesting presentation. I am familiar with software, but unfortunately not familiar with this concept that you presented of injecting defects or detecting defects. So first of all, could you give me a Pullman's explanation to how you inject defects into software? So what kind of defects are they and how are they injected? A quick.
Okay, we can use different type of defects, and we construct a profile of injected defects, and we can inject these defects in software manually or using different tools for automated injection.
So you mean defects like being wrong in doing one mathematical operation, let's say, or is it something completely different, a different kind of defect?
We can construct this profile of defects, and we can use different type of defects. For example, this is shown in calculation or its logical logical problem, or if, no, for example, if you sign plus, but you need to sign minus, for example. So we construct this profile including different type of defects depending on what we use.
And so presumably when a program is very small, you kind of, if you say, for example, it's so small that you can see it on one screen, you can fix all the defects in it, and there are no defects. But as it grows very, very large and it's difficult to test, the defects appear when you don't expect them to. And so this kind of analysis, I understand, becomes very important. So what is the size of software that this analysis is useful for? Where is the turning point, the change? How many, I don't know, lines of code, functions should a program have to be useful or to have a meaning to do this kind of analysis?
And so this question is related to a problem of complexity software and complexity of your model.
First of all, is my assumption, the initial assumption, correct that if you have a 10-line program or a 20-line program, there is no point in doing this kind of analysis? Is that correct, according to your experience?
No, if I understand correctly a question, but this method is software injection defects. It's very popular method, and it use today it use a lot. So it's not only for simple program. It's usually developer use this method for complex program too.
Yes. So this is my question, the actual question. From what point, what is the crossing point from a simple program to a complex program so that this kind of analysis is meaningful?
Maybe I think maybe I don't understand correctly the questions.
Maybe Alex can add.
Yes, Vyacheslav,
okay.
Thank you. I can answer this question because this work represent state of distribution between the state only with use Markov chains. Your question connect with volume of software. It field or this problem is not connected in this work, but is a very important question, and we can depends of our model from size, for example, size of software, number of string in the future.
So, and just to finish this, for training the Markov chain properly, how many fault defects should there be so that you can say that it has conversion, it has some meaningful probabilities that are...
Is a question related to parameterization of model.
Yes.
What about the number of faults which will be injected into code? It's just question concerning parameters from Dr. Nikos Doukas.
We describe only two states. The states of software without injection fault defects. Sorry. And next situation with injection only to position without any parameterization.
Okay, hence in your case you suggested more general models and to take into account questions of Nikos. we need detailized assumption and initial points of the model, including, for example, is the difference between different injected defects. I mean, in point of view severity. And so this is, as we understood, it is the initial model which can be developed, improved, enhanced, considering more detailed parameters and description of assumption. Yeah.
Yeah. Okay, thank you very much.
Mm-hmm. Thank you.
Thank you.
Can I ask a question?
Please.
It's Alexander Lubimov from
Yes.
National Aerospace University. Thank you for the great presentation, Alex and Daria. My question is related to how do you see if all these injections are made in the runtime? How do you see for the real-time software applications? How do you see the impact on the overall software execution cyclogram? How to tackle this problem when you inject errors, and then by injecting you kind of overload the software in runtime, so it behaves differently from its initial kind of cyclogram and timing.
It's not operational.
Okay, Alex, thank you for your question. This question connected with technique for injection, software injection defect. But this this is very known problem. What prefer injected defect in real-time program or software code? It depends on situation, because we have connected with what goals we can receive.
I can add if you would like, concerning question of Alexander Lubimov. This model not work in operation mode. It's a model for testing mode. I am correct, Alexander, Daria?
Yes.
Yes. Can say you, Alexander, asked about about injection procedure in context of operation modes. In this case, this model works just in testing mode, and
Yes.
describe using Markov model process of testing, using fault injection testing.
Yes, it depends on goals. For example, if we want to testing procedure testing in company, yes, fault tolerant mechanism in software. It depends on goals.
Okay, so understand. It's not the runtime.
Yes. Okay. I think yes.
Thank you.
Thank you. Any other questions? No. Can say thank you once more for presentation and for question and answers.